streaming via YouTube. Okay, yeah, then welcome everyone to a weekly colloquium of the Physics Institute of the UNAM in Cuernavaca in Mexico. Our guest today is Dr. Tobias Kießling from the University in Würzburg in Alemania. And yeah, let me say some few words about his vitae. Dr. Tobias Kießling studied physics at the University of Würzburg in Germany and partially at the University of New York in Buffalo. He finished his PhD in 2009 and became afterwards a researcher at the University of Würzburg. Since 2016, he is also managing director of the Collaborative Research Center SFB 1170 on topological and correlated electronics at surfaces and interfaces. His research interests are in the electron and spin propagation in gallium arsenide-based semiconductors, and more recently topoelectronics, a new research field where certain quantum systems are emulated by electronic circuits. So yes, thank you very much for accepting our invitation, visiting us today, at least virtually. Thank you also for working late night for us. I think in Germany it's past 9 p.m. And yeah, we are looking forward to your talk.
Thank you very much. Thank you for the kind introduction, and thank you also for the invitation. Working late is something I think most physicists are used to, so this is not an annoyance, not at all. Yeah, so the purpose of today's talk is to introduce to you what we've termed topolectrics, which really is an approach to topology studied in electric circuit networks. As you've just summarized, research on topological systems is the main thrust in Würzburg, and my background actually is being an optical spectroscopist in semiconductor systems. So I studied these systems basically from day one on when they were introduced in Würzburg, in solid state systems, obviously. And recently, or maybe not so recently anymore, the ideas that were initially used to describe these solid state systems were also carried over to other systems, and most prominently to classical systems. And I will present today the ideas that we had to carry this to electric circuit networks. And as it turned out, these systems are particularly useful also to study topics like non-Hermiticity. So I try to introduce this in the talk as well. Maybe start with a breakdown of what the basic idea of this is, which I'll try to summarize in this slide. So what happens a lot is that when you look at a real experimental system, theorists come down with some effective model that tries to capture the essence of what you look at. What you see here is a major textbook example. So this here obviously is a chain of polyacetylene, and what is sketched here is the famous Schiefer-Heger model, which really is a tight binding model of a one-dimensional chain that describes the hopping between the different sites. And what we're trying to do now is to emulate the mathematics that describe this chain by using electric circuit networks. And maybe a few words on why we chose to go into electric circuit networks. These were mainly two motivations really from my part. So obviously, if you can use a classical system like electric circuit networks, you immediately have a very mature technology at your disposal, which allows you to access a large variety of different components at very reasonable cost, which is something a solid state physicist usually cannot claim. The other thing, and that stems from my second life as a lab instructor, was really a pedagogical motivation, because if I can use electric circuit networks to describe a tight binding Hamiltonian, I basically carry over a microscopic model to the macroscopic world. So if you go back to this slide, you can convince yourself that the experiment that we're putting up here really is very macroscopic. And that is, of course, something that is very intuitively accessible for students. And when I started doing this, this was actually my main motivation to go into this, and it turned into something a whole lot more useful. And that's what I'm going to try to break to you today. So the breakdown of what I'm going to try to introduce today is sketched here. I'll give you a quick account of what an electrical engineer would call nodal analysis in electric circuit networks. something that most physicists don't see in their education, so I'll use 2 slides to introduce how this is done. Then I'll spend a few minutes on the enigmatic Schrieffer-Heger model, which, since I didn't know how many of you are really familiar with the field of topology, in some sense is the harmonic oscillator of the field of topology and covers really the essential ideas. And then I come to the main part of the talk, which will also be the bulk of what I'm going to talk to you about today, which is how we then use the concepts of electric circuit networks to engineer band structures that are otherwise described in tight binding Hamiltonians. And then in the end, let's see how much time we've left. I at least want to introduce how we get non-Hermiticity into the system, which is to say, we also have a means of studying open systems, which then actually breaks over to the field of photonics more than solid state physics. And I'm trying to establish this connection, at least in the very end, a little bit. All right, let's delve right into it. So the idea of nodal analysis in electric circuit networks is to determine voltages on nodes when I have an electric circuit network. The typical setting is something like this, pretty arbitrarily sketched up now. I have some driving voltage which I feed into my system, and then I have nodes which connect by admittances in one way or the other. I can have a ground somewhere, and I'm asking the question of which voltages do I have on these nodes, or reverse, I could ask which currents do I drive. The basic voltage which this is done is the admittance. For an AC circuit, that's the natural quantity to look at. If you're not familiar with the term admittance, that's really just the AC equivalent of the conductance that you would have in a DC circuit. And it connects the voltage to the current the way it's sketched here. Obviously, this will be a function of the frequencies. If you look at some basic textbook examples of components for capacitors, resistors, or inductances, you'll find that in many cases, the response is going to be frequency dependent. And that is something that we actually use a lot. And now what does nodal analysis mean? Now, for a circuit network, you usually define an admittance matrix that connects the voltages on the various nodes via the admittance to the current driven to the nodes, or vice versa. And coming from a more theoretical point of view, and this is how my theory friends actually would also introduce it, you can interpret these admittance matrices in terms of what they call a grounded circuit Laplacian, which in the end is a term they carry over from graph theory, because all I really have here are, mathematically, this is a graph that I connect. And now I can break this into what is called a degree matrix and then adjacency matrix. And for reasons I'm going to describe in a minute, we like to break down our degree matrix into 2 components where we separately put down the ground. And now I'll quickly show you how this is done, which is really not very difficult. If I now take a concrete example and I set up a somewhat arbitrary network of capacitances and resistances, the way this works is, so the first thing I will look at is the adjacency matrix, which now describes how these different nodes A, B, and C connect to each other. And the first thing you can see is that, okay, for an undirected graph, this thing is always symmetric. So what do I see here? This tells me basically how these 2 nodes connect. And if I only have a capacitance here, then 1 connects to 2, or A to B, via omega CAB. CAB is just the capacitance between these 2 nodes, and 2 connects to 1 just in the same manner. And if I then, for example, ask how does B connect to C when I have an additional resistance, that's just going to be the sum of these. The degree matrix basically in the graph theory just tells me how many connections I have there too. Now, in the language of the admittance, this translates into how much current I have to have on these nodes. So this is the total node conductance, how we call it in the end. And there I do the same thing. I can now basically count, okay, how much current flows into this node. Okay, here I have only this connection here. So it's going to be the current that flows in from here. If I do this on this term, I'll have to add what flows over this path, and so on and so forth. And if I now choose to introduce a ground, for example, we put this in a separate matrix for reasons that will be obvious in a few minutes. And in principle, I could plug this already also in the total node conductance, because this just adds to this node, which is the current that I can get out of the ground, or vice versa. So this is it. This is what nodal analysis really does. And that's the language which we're going to use to emulate the type binding Hamiltonians that we see in a few minutes. Yeah, next up, the Shu-Schrieffer-Heger model, just in a very brief account of what it is. So let's look at how this type binding model is set up. If I put this in a matrix form, what this really tries to do is model this hopping of a two-side unit cell, where I can distinguish now between an intracell and an intercell hopping term. And these come with different values that I can tune. And I already chose to put this in matrix form, which is not the most common form to put it down, but it's going to be more obvious to make the connection to the nodal analysis later on if we notate it like this. And then I can do the usual things. If I assume periodic boundary conditions, which is to say this thing is either infinite or connects to a ring, I can translate this into a band structure by a Fourier transform. And very obviously, since I have a two unit cell only, this will give me two bands, and I can find immediately what the Fourier transform looks like, and from that deduce what the energy dispersion of these bands must look like. And now we can discuss a few extreme cases and ask which kind of band structures do we get. And obviously, for the most part, this is going to be an insulator, which is not really surprising because the way this initial model was set up, I have one electron per unit cell. And if I have a double bond, then basically everything is immobile, and that will be intercell hopping to 0. Then everything localizes. That's the full dimerized limit. And my bands will be completely flat because everything's localized. If I now allow for intercell hopping, this will change up to the point that I get a band closing, which would be the metallic case, because now I really can conduct. And then my bands open again. And I end up again in an insulating scenario, but this insulating scenario is now in some sense different. And this some sense is what the idea of topology is all about. So I get two insulating phases which connect via a gap closing that I can distinguish, because what will now happen in this case is that I basically have my dimerized limit such that localizes here. And then I end up with one electron that I can choose to put on the edges. And in layman's terms, that's already what topology is about. So if I have a topological invariant, and we'll come to what this is in a minute, which tells me that my insulating state is topological, I also get to see surface states. And just to introduce very quickly how this is done, I don't want to go into many details here, but the idea is what is called the bulk winding number. I translate this into a basis, which is written in terms of the Pauli matrices, which is really just done in a few lines. If you start from here, break this down in cosine times, you see probably immediately with a physics background that I can annotate that's in terms of the Pauli matrices. And then I have, again, a two-dimensional problem in the dxy plane. And I can translate this now very straightforward, because what this shows me is that, okay, if I show this now in the complex dy plane, then this vector v just shifts me away from 0. And this v basically is a circle around this point to which dvz me. And that's the idea of the bulk winding number, which is sketched here. And now two things can happen. I can either encircle the 0 or cannot. And that will be the distinction between the topological state and the trivial state. I cannot define a state when I just hit the 0 on the circle, which would be the metallic case or the back gap closing. And that's what the idea of topology is about. I can define a invariant that stems from the bulk properties of the band structure, and it will tell me whether or not I have a topological surface state or not in the insulating phases. I think for the purposes of what we have today, this is really all we need. We can then also look at what these band structures would look like. If I have a finite system now, this doesn't work anymore in the nice language of this Fourier transform. But if I just look at how these states evolve into bands, then we can sketch here exactly the situation that I just described. If I assume a fixed intercell hopping of 1, parametrized, we see that as long as the intercell hopping is stronger than the intracell hopping, we'll get to this case where we have the edge state on the sides. And if I look at the localization of the states, this can also be seen here. And if I then go beyond the gap closing, I go into an insulating regime again, but now I don't have any zero states anymore. And I can also no longer see any localized states at the edges. And even in the localized regime, I can, of course, have bulk states, which are delocalized over the system. So that's the bottom line. This is what this model looks like. And now in the next step, what we're trying to do is really build a circuit that behaves like what we've seen here. And just by formal analogy, it's straightforward to see that in order to get something like this, what you would like to have is a hopping type picture, where you now reproduce two different values, now in terms again of admittances, which are interchangeable. The minus isn't very important. I just kept this in for consistency reasons. What is important is that I'm trying to go into a regime where I interchangeably have different admittances between the nodes. Now, if I'm trying to set up a real system, obviously what I'll have is a chain at least of some length n, which I can choose. And now I have to think about how I do this in practical terms. And I'm trying to express this again in terms of the admittance matrix that I've looked at before. And if I do this now in this setup, so the first thing I can do again is look at the adjacency. So that already looks very much of what I would want. If I go up in a system where I just interchangeably use two values of admittances y1 and y2. But for the total node conductances, I now get something which is not really zero, which is what I would actually like to have to build the system. And in particular, I also get a different value on the corners than I get for the rest of the diagonal elements. And this is now where the benefit of using a different notation for the grounding scheme comes in, because what we'll now do next is use a proper grounding scheme to get a unidiagonal, because that will then allow us to break this down into something that basically splits down into what I want to have, plus some constant offset. And that's the spirit in which we now design these matrices to mimic tight binding Hamiltonians. And now we need to think a little bit harder in terms of is a situation in which we can forget about this part. And this is already telling us that probably going to resistances, real resistances, will not be the road to success, because that will always generate some finite number here. But if I, of course, now go ahead with inductances and capacitances only, I can actually generate a regime in which these two values exactly cancel, and I end up with something that looks already an awful lot like the Schuschneider Hamiltonian. Yeah, and then this is the implementation that we actually went for. This was the initial idea, and this would now be done in terms of capacitances and inductors. And I'm going to rewrite this a little bit in terms of the resonance frequency, which is then probably also a language that is a bit more familiar with what you will see on most textbooks. And the reason we do this is because that also is a already practical feature that we implemented that is a little bit more obvious from this type of presentation. So what we've now chosen to design is a one-dimensional chain with interchangeable capacitors, all nodes connected to ground over an inductance that we have to choose appropriately. And now by deciding in which node we feed the driving current, we can actually basically decide in which of the two phases we end up. That in this sketch, if I go from 1 to 2, I'm basically changing C1 and C2 in their position, and that means that this hopping element will just go over into 1 over the value that it previously had. And that is a very easy way to switch between the two insulating regimes and then to study both on one and the same circuit board. Yeah? So that was the straightforward idea. And it's clear that if we do this at the frequency of resonance, which we give here, these diagonal elements vanish altogether. And that should get us to a situation in which the voltage response of the circuit very much resembles of what the Schur-Schiever-Heger model predicts. If you want, this was the hour zero of this entire endeavor. This was an idea that was initially brought forth by my colleague Ronnie Tomale and in close collaboration with Jingwu Ali from Singapore. This was back in 2017. Stefan Imhoff, who is the one responsible for most of the experimental results that I'm going to show today, coupled together this circuit board. This is the initial design, which we then manufactured actually in-house and set it up. And this is it. So this was the birth of the first Topolectric experiment which we did. Yeah, and then we did a few obvious experiments to study what's really going on now in our system. And the first thing that you want to look at, obviously, is the question of whether or not we can see a mid-gap mode appearing. Now, I should say just a few words about the experiment, not to go into too many details. In practice, what we're doing is we're not measuring currents, but we're feeding in currents and measuring voltages. That's just easier to do. That means that we have to invert the admittance and in practice calculate a 2-point impedance, but that's a technicality and conceptually not very important. So I'll not talk about this a lot more unless there are really detailed questions to the experimental technique. And yeah, that was more or less an immediate success. So you can see here, so for the region in which the intracell hopping is smaller than the intercell hopping, we will see this appearance of the edge mode as predicted. And if you jump to the other configuration, it just disappears, as you would expect. Now, of course, that in itself may be rooted in other things, so there are more things to look at. And one of the first things that we wanted to look at is how does the state really localize? And that actually, coming back to what I said initially, was also the idea that I had when I introduced this, because while it is notoriously difficult to look at the localization of a wave function in polyacetylene, measuring the decay length of the voltage, if I feed this locally to the edge, can be done by any student in the lab. And then just with a little bit of math, you can convince yourself that the wave function should die off depending on the coupling strength T. And that, of course, we can translate back into the values that we fed in, and we've obviously measured, and the result is this. So this is now normalized to the feed voltage that we see on the edge mode with which we go in. This is something that you can very easily measure with equipment that is available for any undergrad lab. So yeah, a dynamic range of 5 orders of magnitude is not very challenging. And you can see that the resemblance is remarkable. So this was something that got us very happy, and actually then was also the first thing we published. And after that, we got a bit excited and asked, okay, what else can we do with it? And the next obvious thing that you then really want to do is look at band structures. So for that, the experiment becomes a bit more tedious. I'll just break down how it is in principle done. We don't have, so we need to be a little bit careful, because what we don't have is a real unit of distance. This is a graph, so we're connecting nodes. So we cannot, what we do not have is something like momentum space in the end. But what we still have is translational invariance. And that is the only thing we really need to connect a periodic system, so under periodic boundary conditions. And we can still run by the same logic a Fourier analysis and find something that resembles what would be a band structure in a real hopping Hamiltonian. And that was the next thing that we've done. So for that, now you need to feed into the individual nodes, you measure the voltage response over all nodes, you repeat this, and obviously this now becomes more time consuming. So this is when we first started to think about sizes of our systems and how we maybe can do this in parallel. But for the purposes of what I'm going to show in terms of results, this is actually, this was no longer that straightforward, but it's also not magic. And the key result, which you see here, is now if you play around again with the tunings, we can very nicely reconstruct what you would expect in terms of band closing if we go really to equal couplings, and then we can tune ourselves on either side of the topological transition and basically get up any band structure that we want. So this works very well. Now I'm just going to flash a few of the other systems that we've looked at to give a bit of an overview of which types of systems we can now study. In principle, this is now an open playground for pretty much anything that you want to do. Getting this to higher dimensions is conceptually straightforward because dimensionality really is defined in this system by the number of nodes you connect to a specific node. So in principle, you can run this even to dimensionalities very much above 3. This is not something that is conceptually difficult. Getting it practical, though, is a different question because now you need to, so the way we've done it initially, then we would just connect over BNC connectors from side to side and had to reconnect every single thing. And then, of course, if the system really becomes higher dimensional, you very quickly have many, many thousands of measurements which you need to do. And that's using multiplexers to parallelize this. This is something where you have to be carefully adjusting now the input impedance of these multiplexers to not interfere with the circuit in a way that you actually change the circuit. But that all can be done after careful considerations. And I just want to show a few results of what we did. So another straightforward experiment to go to coming from the SSH chain was actually to study graphene, because that really just forced us to basically extend what we've done in 1 dimension to 2 dimensions, but otherwise not really change a lot on the circuits. This would be the unit cell that I sketch here. And I just want to summarize. I'm not going to show this in the great detail I did for the Schiefer-Heger, but it follows the exact same conceptual logic. So you would set up an adjacency matrix that describes the hopping Hamiltonian that you have in graphene. On a side note, you can do this for honeycomb and brick wall configuration. That's an aside. I'll stick to that. You can see here what we've done now is go through the, again, band structure of the graphene circuit. I show this in this 3D map to see what the difference between the red and the black points really is. These were just different paths that we've taken through the Brillouin zone. And if you color code it here, despite the fact that we don't really have a proper unit of length in the system, you very much get the resemblance of the honeycomb pattern that you're used to. So this works very well. And yeah, then you can do other things. You can go around and basically extend your system periodically in 1 dimension and have edges on the other dimension. And depending on how you choose the termination, it can be zigzag, bearded, or zigzag bearded. And you get all these nice configurations that you would see from now, while we got carried a little bit away with this, at this point we started asking the question, okay, while this is nice and doable, how much did we really learn from it until here? Because yes, we reproduced a whole lot of things, but these were really things that have been known. And the reality is, this is a sort of criticism that I'll take any day, because all we've done so far is convince ourselves well behaved. If this is something that you can also easily just simulate something like LT Spice and it will just work fine. So the obvious next step to get anything useful out of that was to go into a realm where linearity would maybe no longer be something that is accessible, or maybe go to systems that are not straightforward, introduced in solid state system or photonic system and the likes. And one of the first ideas we touched upon, albeit still linear, was exactly in that spirit. That was also one of the early experiments we've done, and that was now going to a system that would represent a higher order topological insulator. Now, what is that? In the 1D case, we've seen 0D localization on the edges. So the systems that I usually work with are either 2-dimensional topological insulators or 3-dimensional topological insulators, and then that means that the topologically bound state is 1-dimensional lower than the dimensionality of the system that you investigate. These higher order topological insulators, they actually describe a regime in which the dimensionality of this topologically bound state are reduced even further. So if we now go to a 2-dimensional system, that would correspond to a system in which the state is really localized at a corner. And that is something that has not been established so far in a solid state system. And quite frankly, it's not obvious to me that it can be. We've been juggling with ideas for a while, but say the requirements that theorists put down on a real system to do this are not something that is experimentally easily met. So this is why we stuck to linear circuits for a little longer. And I should also say that something I haven't discussed a lot here, but coming from solid state systems, the topology very often roots in the Kramer's degeneracy of fermions, and then the concept of topological protection is extremely robust because that's something that you can fundamentally not break. So as long as you don't screw up the symmetry of the system too much, this system will really host the state under many circumstances. Go into a classical system, that is not true, because now really to see the topology, you need to establish the symmetry that you require to have your system behave the way that the model Hamiltonian that you're trying to emulate really demands. So this was also a testbed system in this regard, to see under which circumstances and how much impurity, if you would like, in the language of a tight binding model, your system can take and still contain a state like this. And yeah, the basic result is summarized in this slide. This still works very well. So this is what the calculation actually told us that the spectrum of our circular Plascian should now look like. Since the system is already quite extended, there are many, many modes. So this is no longer that straightforward. But in terms of robustness, this is still really well behaved. And you can also see this here. So this bulk frequency that connects to this corner state is very visible. If you look closely, you can see that there are differences in the bulk, which stems from the fact that now the real system comes with spread, comes with impurity, comes also with nasty couplings that I guess most electrical engineers would have expected, but we had to learn the hard way are there. And you can play the same game that we've previously done with the Schuh-Schrieffer-Heger model and ask how does the localized corner state die off if I go deeper into the system. And again, this is a very well-behaved system. So in that sense, electric circuit networks are a very nice platform to study also these higher order topological insulators. So with that being said, I'd like to leave the realm of linear systems and just arbitrarily jump to one of the experiments that actually have a very proper connection to optical systems. And in particular, what I would like to study now are open systems. Now, open systems are something which are not inherently new. There are many established formalisms that can describe them. Optically, one very often uses the Lindblad master equation approach. But what has been also been looked at in recent years in more detail are non-Hermitian Hamiltonians. And in some sense, there are, if you like, the more natural way of describing a physical system, because a Hermitian operator always assumes that I have a closed system. And for many solid state systems, that's a reasonably well met assumption. But actually, most real systems connect to the outside in some sense. So there's always some sort of loss. And the moment you have loss, basically, one way to describe this is non-Hermiticity. And we actually, so then maybe on a side note, that's seminal work by Bender and Tang, that it has been known for a while that as long as certain symmetries are pertained, in particular parity time reversal symmetry, even non-Hermitian systems can produce real-valued eigen spectra and are therefore a proper resemblance of even closed systems. So non-Hermitian as per se is maybe not that hard a requirement, but what is really interesting is if you introduce non-reciprocity. And with non-reciprocity, we basically mean that we now really have open systems in the sense that we have loss and also gain. And that's one of the big benefits of the platform that we are using. Loss is something you can introduce easily in most real systems. Gain is not so straightforward, but it's of course something that you can very nicely do with operational amplifiers and electric circuit networks. And now again, I'm going back to the Schuh-Schrieffer-Hager model because I've introduced this at length, so it's most easily accessible for this type of model, what we will now modify. We will still have an intercell hopping and an intracell hopping R, but the intercell hopping will now modify in a way that we introduce an anisotropy. And this anisotropy is actually the key ingredient now to the non-reciprocity. We will again set up a chain, which we then can study either in periodic boundary conditions by connecting it to a ring, or under open boundary conditions by just grounding the ends. And the key is now how we set this up, which is what I quickly sketch here. And the key component that came now in is this INIC, which I want to sketch in a few words. Everything else basically remains the same. Here we still have this intercell hoppings represented by capacitances, and we have the reciprocal part of the intracell hopping represented by capacitors and inductors. The details of why we now chose to introduce an inductor are conceptually not important. Technologically they are, but conceptually they're not. And the key ingredient is now the INIC, which is an abbreviation for a negative impedance converter with current inversion. And I quickly sketched what this is here. So this is basically a operational amplifier in feedback configuration. And depending on how I choose now the values of the impedances here, I can set up different amplification regimes. And it's straightforward to see why this is a negative impedance converter with current inversion. If I equal these two, then this will just turn into ones. And compare this to what I would get from just feeding the same thing to an impedance Z3. It's a 2-line, 3-line calculation to set this up. So I'll spare the effort here, but you can convince yourself in no time that this is the proper representation of the circuit. And the basic change that you can now see is that, I left changes sign in this configuration with respect to just going into regular impedance. What this means is that the amplifier now responds different to voltages from left and right. It will attenuate from one direction, but it will push current into the other direction, and that's exactly what we want. That's exactly what we tried to set up. Going back in this scheme. Yeah, then the reality is that this is a configuration that most engineers will tell you not to go into, because now you're driving your system into an unstable situation, because it's very easy to do nasty things here, like saturating your operational amplifiers, or basically going out of the linear regime. And now at this point, it becomes important to really look at the detailed properties of the operational amplifiers and think about which values for the impedances you really want to have. You also get oscillations into the system very easily, which is why we chose to modify the design a little bit. But once you work this all out in a careful fashion, you can actually end up in a regime in which this setup really represents the model that we want. And this is now the response that we will get to it. And this is already one of the main results that these non-Hermitian systems really host. So what you see here now is a very obvious and very pronounced non-local voltage response. So what we show here is how the voltage will build up on the nodes depending on where we actually feed the current. And what is always clear, even if you feed the current directly in node 1, there's practically no voltage buildup in node 1. But it looks like all states shift to one side of this chain. This is obviously done in open boundary conditions. And this is exactly what has been predicted by Yao and Wang in this paper here, which is what they call the non-Hermitian skin effect, that in a non-Hermitian system, what will happen is that under certain circumstances, all modes will extensively localize at one side of the system. So even all bulk modes will move out there. And this is exactly what you can already see on this slide. The term is a bit misleading, I should say, in that, in particular, if you use electric circuit networks to study that, this non-Hermitian skin effect is in no way related to what the electrodynamic skin effect would be. It just refers to the fact that I push my states to the surface, and in that sense is a skin effect, but the physics responsible for that are really very different. And yeah, you can do the same things. You can look at what you would expect for the build-up for these voltages on the nodes as a function of the feed, and again we end up in a situation where the emulation really resembles very nicely what you would expect. Now you can of course do more things. We can basically now study many things. I chose to just show this bit. Obviously, if I go to a non-Hermitian system, my eigenvalues will no longer be real valued. So we now have to acquaint ourselves to look at complex valued eigenvalues. And what is shown here is the red curve would be what the model expects for a periodic boundary condition situation in which I just close the ring. And the green situation would resemble the situation that I have for open boundary conditions. And now what we can, of course, do in the experiment is just take a ring and use one connection here that we then, in a controlled fashion, break down, going all the way from the periodic boundary condition of the ring to the open boundary conditions of the chain. And we can look at the spectral flow of these modes, how they should develop going from one regime to the other. And this is what's shown here. And again, this is very much resembled by what the model prediction shows us. And we then can, of course, also look at the localization of these states and see how we go basically from a delocalized regime to a regime in which this is completely, again, localized to one edge, which is what we see previously. Yeah, and with that, I'll maybe leave it in terms of introducing what we can do, and maybe do a quick jump to where this can also be useful in other systems, because while it's nice that we can reproduce it like this in our model system, what is this actually good for? And there's an extremely nice experiment in photonic systems done in the group of Alex Samite, where they basically used the exact same setting in fiber networks, which they coined funneling of light, and the exact same idea has been used here. So this is the resemblance of the system, where they get anisotropic coupling, and they do similar things like we do, the anisotropy. It's a bit harder to introduce anisotropy in a photonic system because getting real gain is a challenge. So they would play with things like loss and less loss, which is then effective gain. But the essential physics are very similar. And that is, of course, now something that is extremely useful. I mean, what ideally you would like to have is that you can use many, many, many modes that you can couple into one mode. And that would have real applications. It's something we could use. And we're in close exchange with this team. I mean, this is what we're trying to really strengthen. And this is ultimately where our systems could be useful, because setting our systems up is a somewhat very much cheaper version than what is required here. And if we can learn basic pitfalls or shortcomings of the models before we're trying to implement it in a powerful platform like this, that's just a very useful way of getting our hands onto functionality. Yeah, with that, I think I'd like to acknowledge a few people. So that'll first be my own team. Most of what I've shown today, as I've already said previously, has been done by Stefan Imhoff, who's about to graduate now. He's been the experimental first waiver, if you like, and is now succeeded by Hauke Brandt, who's been doing a lot of this work recently in hyperbolic systems, which is something I couldn't touch today. Fleur and Bayer, Johannes Brehm, Vladimir Markovic, Christian Berger have all contributed to this work in some variation at some point. I'm obviously extremely grateful to Lawrence Molenkamp. We use a lot of his lab infrastructure, and I'm extremely grateful that he offers me the possibility to use his vast and impressive lab infrastructure. And then obviously I should like to thank our collaborators. That is foremost Ronny Tomale. He's the, if you will, he came up with the most important ideas that we've been following for the last years, together with Qinghua Li from Singapore, his team Martin Greiter, Toby Helwig, Alex Stellmeier, and Toby Hoffmann, who really are excellent PhD students. A great thanks also to Titus Neubert, and obviously to Alex Samait, and then obviously also to the funding agencies who've been supporting us over the previous years. That's actually exclusively funded by the Deutsche Forschungsgemeinschaft. Most of my funding comes through the SFB 1170, but I'm also extremely grateful to funding from our cluster of excellence. And with that, I'd like to close it down. Thank you for your attention.
Okay, thank you very much, Tobias, for this wonderful talk. I enjoyed it very much. Yeah, very interesting work. Are there comments, questions from the audience? If so, you can raise your hand and switch on your microphone, or you yeah, there's a question from Alex Franco. Alex, if you like, go ahead.
Hi, Tobias from San Luis Potosí. Thank you very much for your conference. It was very interesting. And I have two questions and a comment. If you think all these LC circuits, one thing which is very difficult for me, coming from a tie-binding Hamiltonian, is to understand what is the idea of atom. Is the LC circuit, I mean the LC is the atom, and what is the coupling? Is the capacitor, is the inductor, or is a mixture? I didn't get it.
Okay, I'd hope to have made this clear by this slide here. So in that sense, I think it's somewhat easier to spot. So these off-diagonal terms, which we encode in the adjacency matrix, they correspond to the hopping terms. And what we would have on our total node conductance, that would be in the language of a type binding Hamiltonian and on-site potential. And I think in that sense, it's clear what the correspondence would be. Does that help?
Yeah, it happens. Well, because at the beginning I wasn't here, so sorry. I'm sorry. Yep. Maybe I lost this part. Yes, sorry. It's my mistake. And another question: electron-electron interaction can be of systems, or you have to do something more nonlinear to introduce electron-electron interaction.
Yes. So this will not work in this simple setting that I sketched today. So I'm not doing this. You could think about, again, introducing nonlinearities that do this, which works. I mean, something that I've also not shown today is we've worked on active circuits as well. These kind of things you could in principle think of, but honestly, it's not something that we've worked out. So that's something we'll have to think about.
Yeah, it is very difficult. Yeah, very well. And my comment is, you say during your talk that there is no idea of length. It's not appear here in the LC circuits, but maybe in microwaves you can extend the same ideas and introduce the idea of length. It's just a comment, right?
This is a very good comment, and I think has been in part also been done. So actually, before we started this, there was work by Jonathan Simon, and they've looked at microwave resonators. Their experiment is much more elaborate because they don't have galvanic coupling, so the measuring on their part is more demanding. But you're right, and in these systems, it's easier to get a handle on something like a measure of a unit of distance. having said a shortcoming so far for us, it's just something we need to keep in mind, so that the analogy only carries so far.
Okay, thank you very much, Tobias.
Okay, I have a quick related question. Inductors are connected to ground, and here I don't see the connection. Right, if you go one slide back, I don't see the connection of the impedances Y1, Y2 to the ground.
Here we didn't do it. So this is to motivate this. I just wanted to note down some deliberate Y2, which is sort of arbitrary and looks fairly diagonal here. But if I now really want to be able to tune these on-site potentials or these degree matrix knots also to 0, I need to introduce a inductance that compensates the inductances coming in from these two nodes. And this necessitates why, so if this, I really want to have this term to live on all nodes. And by that, I'm forced to also introduce inductances to ground, which I've not shown on the previous slide. So this is now if I really try to come up with a real physical implementation rather than just a conceptual sketch.
Okay, thank you. Another quick related question. And can you make this simple circuit, let's say, on a breadboard? Can you buy these, let's say, these capacitors, inductors, and measure with an oscilloscope these things? Or
this is exactly what we did in the beginning. Yeah.
Okay.
So a few things that we learned the hard way. So there are a few design principles, and in brief, they are always try to go to as high frequencies as your systems allow you. I mean, that's somewhat obvious because the noise will just reduce. One thing that we had to fight a little bit was spurious inductance. So I should say actually inductance. So maybe going back to this slide, you've seen that we've used insanely large coils, mostly because they were available. And we wanted to do quickly. That turned out to be a bad idea because they nicely couple inductively. And then you see then you see very different signals than what you expect to see. So these kind of things you can screw up, but in principle, this is no black magic. So in particular, as long as this is a 1D chain. I should maybe also add, which is a real change for my life. This is a room temperature experiment. What you maybe can just witness a little bit in the back here is an optical cryostat. So most of my life happens at 1.6 Kelvin experimentally. And that is really beautiful for a change to get something into your lab and just have it running.
Okay, thank you very much. There are other questions from Carlos Gonzalez. Carlos, if you like, switch on your microphone.
Yes, thank you for your talk. It was wonderful. Very great job. I was wondering, well, you already mentioned it. All of this is working at room temperature, right?
Absolutely, yeah.
You also mentioned something about the nonlinearities, right? Introducing nonlinearities in the transmission lines. Is it in the same fashion, like in circuit quantum electrodynamics, like a Josephson junction, for example, in this kind of systems? So the general answer is, of course, yes. So maybe before jumping to Josephson junctions, a more straightforward approach is to use something like diodes, or in particular, varicaps is something which we've also been studying. We have a recent publication in which we started the Korteweg-de-Vries equation using these types of settings that didn't connect to the topics that I wanted to touch today, but that's something that can absolutely be done. And this is also actually what we've been doing for the last 2 years mostly, because really the interesting physics happens when you leave the realm of linearity. Interesting. I see. So it will be because I mean there is also this whole community of circuit QED and waveguide quantum electrodynamics working also with quantum circuits, which works at near the zero temperature where quantum fluctuations are important. So yeah, that's my question is related to that. It's because I mean one of the things that these people is interested in is in, for example, establishing, for example, long-range interactions between two separate quantum systems mediated by the interaction with the transmission line, for example. Maybe we can think about some long-range interaction mediated by these classical circuits for two separated classical oscillators, for example, or something like that. I don't know. I'm just thinking loud.
Absolutely. Maybe I can go to a spare slide, because there's only so much you can cover, but there's, of course, so this is something which I think is maybe not unrelated to what you just said. So this is also an idea that we've been following for the last 2 years or so now. So since we don't have a predefined unit of distance, we can actually turn this into a feature. And an idea that came about was to study hyperbolic space. Now, of course, no one can study hyperbolic space in Euclidean space, but what we can look at is a Poincare projection of a hyperbolic curved space. And then we can emulate the change in distance by changing the strength of the coupling. And I think that's very close to what you just said, that I'm trying to now distinguish between short range and long range interactions. And that's an experiment so what we've done here, actually, this is slightly different. It's written up here. So what we've now looked at is the actual temporal evolution of a signal that we feed into one point of this circuit. And of course, now the time evolution will be very different whether or not you're in Euclidean space or something that is curved. It will propagate in different directions. And this also works extremely well. So this is certainly something we could investigate further if you have a specific model in mind. I mean, that's something to discuss.
Wow, it's really interesting. Okay. Oh, thank you very much. Yeah, it's really wonderful work. Thank you.
Thank you.
Okay. There is another question from Parisa Machari. She wrote the question here in the chat, and I will read the question. My question is that if you can
the answer is we haven't come up with a way yet to do this. This is, if you could do magic angle graphene, that's of course something that would be beautiful, but now that would require us to interfere different lattice layers, and we haven't come up with a clever way yet to couple these different layers in a way that it would well resemble what is required to do that. So yeah, it's a beautiful idea. If you have a conceptual way of doing this, please approach us. We'll be happy to build a circuit in no time. We haven't succeeded in finding a proper way of doing it yet.
To this one, what are the limitations of size of the system? So to how many atoms you can push this?
So one thing which we've changed now. So in the beginning we were building every board for a unit cell, and then we would just build so and so many unit cells and maybe connect them in a ring or terminate them to get some boundary. It turns out that the necessity of building many of them for a periodically bound system is completely unnecessary. So what we started doing is build one unit cell and then add an analog multiplier, which basically connects back into K-space and allows us to basically go through K-space over and over again. Periodic systems. For non-periodic system, it depends on the dimensionality. So in terms of practicality, I would say 100 nodes is handleable. Now, Stefan Imhoff probably would violently disagree, but that's maybe the change of perspective from PI to PhD student. Anything beyond that, I think is probably not that we're doing now. And that's the big asterisk of approach to it all. So this is really, at this point, still extremely low profile, low budget. If you have an interesting question that requires larger systems, the next step is graded circuits. At this point, of course, it's no longer a cheap experiment, because now you need technology, you need overhead. But now system size is again not an issue. You have something like 300 billion transistors on your chip for your cell phone. So I guess the answer really is here: how interesting a question is it, and which overhead does it justify?
Are there further comments, questions from the audience?
Can I ask one more question?
Yes, go ahead, Carlos.
Yeah. Sorry. If I think about, I mean, like your network, right, of classical oscillators or transmission line or whatever. For example, I can think about this system as an environment, right, as a bath, with density that characterizes this environment, right? So can you engineer like this spectral density, like in the general sense, like can you make like any spectral function that I give to you, for example, like if I tell you, okay, I need this bath, this environment with for example, with a parabolic spectral density, can you make it?
Well, I guess again it depends. So I'm always hesitant to say just yes and no. So it really depends on the details. So I would reverse it. I would ask the question: what is the question that you're asking to the system? Yeah, because for example, if you look at band structures of finite-sized systems, then it really breaks down to how many nodes do I have to implement to have the resolution that you need to answer a specific question. And then if you exceed a certain scale, as we just discussed, this will just not be practical with easy available resources. Yeah? So
I see.
It really depends. I mean, if you have a specific question in mind, always hit me, and we will be able to give an answer on a specific question. But for a generic question like this, it is just difficult. Huh?
Yeah, I see. Okay, thank you very much. No, I'll definitely get in touch with you if I can.
Please.
Thank you.
Okay. Yeah, thank you very much. Are there further comments, questions?
My mic is working now. Can I ask my question?
Yes, of course. Parisa, go ahead.
Regarding to the previous question, you look at to the band gap in this presentation. But do you think, is there any other method that you look at to the transition of the electrons? And if you can emulate it, do you think, can you use it in some electronic devices?
So I need maybe to answer this right away. So what we should be careful about is, so we're getting a formalism that gives us a parametric representation of what a band structure would look like in a type binding model. What we don't have is a population that lives on that. So in that sense, we cannot build something like an exciton and ask how does this thing propagate through the system. If we're talking about many-body effects, we really would have to think about how these interaction between the modes would renormalize the spectra. These are things that we can emulate. What we cannot really emulate is a bound state.
Okay, thank you so much. And the other question is related to this slide. This is a Poincare disk, and you can emulate the negative curvature with that. Okay, then after you emulate the negative curvature, what will be the next step?
So this is now work that I should have, if I had known that the questions come to this, so that I should have included a acknowledgement also to Anthony Chen and Igor Böttcher, who have been doing a lot of this work. So I should maybe refine one thing a little bit. What we really look at is the Poincare projection of the curved space. So we're not looking directly at the curved space, but we can of course now do things like ask questions like which point group representations are possible in Poincare's, very much in the way that you would do this in Euclidean space. This is actually something which the mathematicians call the Fuchsian groups, and these are things that we can measure. Then using this logic, you can use things like you can ask yourself, how does graphene look like if it lives on a parabolic space, and how does that modify the structures that you see? That's actually something we've done. So questions to this extent are addressable, and of course we only started doing this, and the hope is that we can do more exotic things. So one thing we've been playing around with is can we measure things like dispersion relations of super realistic particles, for example. I mean, the idea is always the same. So in principle, we can use our impedances to emulate complex valued structures, I should say. So if I look at some model of gravity and I have a complex valued mass, that's something we could actually emulate.
Yes, thank you so much. Thank you for your nice talk.
Okay. Yeah, I have yeah, a related question to this work. So there are some ideas of deforming graphene and let's say to emulate by this deformation. Then you have in graphene ultra-relativistic fermions which move in a deformed space, and then you can emulate, let's say, to be very emblematic black holes who trap. Could you imagine to do something like this with this circuit emulation? Because you said you can tune widely the coupling of the sides in your system, because this always has been some problem with these ideas. You cannot, real graphene, you cannot deform it that strongly to go into this regime where you, let's say, emulate a black hole or things like that. But well, we don't have real graphene here. We can, if I understand correctly, we can tune in a wide range the coupling of these sides, and maybe one could things like that in the circuit systems.
I mean, that's something that would be absolutely worth looking at. I'm not sure about so with graphene, we can certainly think about doing it. I don't remember how exactly they termed it. So I know there's a paper by a Chinese group. They actually looked at how an event horizon could be emulated in a circuit. I don't think they actually built a circuit. At least I would have to double check, but I certainly think there's a calculation on that already.
Okay.
So these things are very actively considered. Yeah.
Okay.
Happy to discuss this further.
Let me think and let me look up this paper. But it goes just in that direction, which I try to ask. Okay, yeah. Are there further comments, questions from the audience? If this is not the case, Tobias, once again, thank you very much for this wonderful talk. Very nice, very interesting. I enjoyed it very much. Working late night for us. I think now it's past 10 in Germany. You should go home. Okay, and yeah, and we will go for lunch, I think, here. Thank you. Bye-bye to everyone. See you next week.
Thank you. Bye-bye.
Bye-bye. Okay. Ja, ich muss da nochmal, das geht genau in diese Richtung mit diesen Event Horizons, die man also wir haben da so ein bisschen gearbeitet, einiges drüber gearbeitet.